All right, welcome to the deep dive. Today, we're going deep on something that's pretty fundamental to modern computing. How to squeeze more performance out of virtualized environments.
Yeah, virtualization is huge these days, right?
Absolutely. But the sources we've got here point to a big snag, the way virtual machines typically handle input and output, the I/O. It can really bog things down.
I/O is always a bottleneck, isn't it?
Seems like it.
Yep.
So we're going to delve into single root I/O virtualization, SR-IOV, specifically in PCI Express. See how this tech aims to tackle those limitations head on.
Sounds like a good plan to me. The sources you sent over really emphasize just how much we rely on virtualization now and how those traditional I/O methods, well, they're not exactly cutting it, especially as we keep pushing VMs to do more and more.
So true. So let's break this down a bit. What's the core issue that SR-IOV is designed to solve? Your sources keep mentioning traditional I/O virtualization where the hypervisor is kind of stuck in the middle of all the hardware communication. What's the problem with that?
Think of it like this. In the old way of doing things, every single bit of data going into or out of a virtual machine has to go through the hypervisor.
Like a traffic jam.
Yeah, pretty much. The hypervisor has to pretend to be the hardware for each VM. It acts as this middleman, this software go-between for every single I/O operation.
So every time a VM needs to read or write data, it has to go through this whole process.
Exactly, and that puts a ton of stress on the host CPU. It has to manage all these virtual devices and translate each I/O request. Plus, it adds latency, delays in data transfer, and in the end, you can't run as many VMs on a server. And the apps, especially the ones that rely on lots of I/O, they really suffer performance-wise.
Makes sense, like pouring water through a sieve.
Right.
It works, but it's slow.
Exactly, and that's where SR-IOV steps in. It's a hardware-based solution, a different approach altogether. It's defined by the PCI SIG as an extension to the good old PCI Express standard.
So getting the hardware involved directly.
Yeah. What's cool is that SR-IOV lets a single physical PCIe device, like a network adapter, basically masquerade as multiple separate physical devices.
So one card can act like many.
Yep. And each of those virtual devices can be assigned directly to a VM. And get this, the VMs can then access these virtualized hardware functions directly. They bypass the hypervisor entirely for the actual data transfer.
Wow, cutting out the middleman completely. So instead of the hypervisor shuffling all the data around, the VMs get their own direct pipeline to the hardware.
Exactly. And what does that give you? Well, first off, a big boost in performance for the VMs. We're talking speeds much closer to what you'd see on a physical machine, no virtualization involved.
Like it's running on bare metal.
You got it.
Yeah.
And since the hardware's doing the heavy lifting, you're taking a load off the host CPU. So what happens then? Improved scalability. You can cram more VMs onto the same server without everything grinding to a halt.
More bang for your buck.
Exactly. Plus, you get better isolation and security between the VMs that share that physical device. Lower latency, more efficient use of the hardware. All good things. It's all about making VMs act more like they're running directly on the hardware.
Okay, now your sources keep mentioning these things called physical functions, or PFs, and virtual functions, VFs. Can you break those down for us? What exactly is a physical function in this whole setup?
Okay, so the physical function is the main fully featured part of an SR-IOV-enabled PCIe device. It's like any other PCIe device. The system can see it, manage it, all that. The big difference, the PF is, well, it's SR-IOV aware. It knows how to do virtualization.
So it's built to handle this from the ground up.
Exactly. And the PF tells the system, hey, I can be virtualized. It's in charge of setting up the whole SR-IOV thing, including creating and managing those virtual functions we'll talk about next. Usually the PF driver hangs out in the hypervisor or the host OS, acting as the control center for all the virtualization stuff.
The brains of the operation, basically.
Exactly. And here's another interesting tidbit. A single physical card, like a network card, can actually have multiple PFs, up to 8 in some cases.
So one card, many brains.
In a way, yeah. So the PF is the boss, the administrator for everything virtualization.
All right, got it. So the PF's calling the shots. But what about those virtual functions, the VFs? Where do they fit into all of this?
So the VFs are like little slices of the physical device, lightweight virtualized instances, each with the direct connection back to their parent PF. These are the guys that actually get assigned to the VM.
So the PF creates these VFs, and then each VM gets one.
Pretty much, yeah.
Yeah.
Now, here's the catch. A VF shares the physical resources of the device, the memory, the actual network port, whatever it is, with its parent PF and any other VFs from the same PF.
So they all have to share. Doesn't that cause problems?
It could, but here's the clever part. each VF has its own dedicated PCI configuration space. It's like a set of hardware settings, and it makes the VF look like a totally separate physical PCIe device to the VM's operating system.
Ah, so the VM thinks it has its own dedicated hardware.
Yep. And those VFs are built for speed. Data transfer is their game, and they need minimal configuration. And a single PF can support tons of VFs, sometimes even hundreds. The key takeaway here is that the VFs provide that crucial direct hardware interface for high-performance I/O, completely bypassing the hypervisor's software layer for data movement.
So the PF sets up the playing field, and the VFs are the players running the ball, so to speak. They do the actual work of moving data in and out of the VMs directly with the hardware. Now, there's this PF-VF relationship that your sources keep bringing up. It sounds like they need to work together pretty closely.
Absolutely. It's a top-down kind of relationship. The PFs are in charge, managing and supervising the VFs. So the PF driver, which usually lives in the host OS or the hypervisor, is the one dealing with the physical hardware and making sure those VFs are enabled and configured correctly.
Makes sense.
But on the other side, you've got the VF drivers. They live inside the guest operating system of the VM. They're what let the VM actually talk to its assigned VF directly. So while the data can flow straight between the VF and the physical device, setting everything up and some management stuff, that still goes through the PF. It's this separation between the control plane, which the PF handles, and the data plane, which the VFs manage, that makes everything work so efficiently.
So how does a VF actually get created and enabled? It's not like they just magically appear, right?
Not quite. It's a multi-step process, and it happens at different levels. Usually it starts with enabling SR-IOV in the system's BIOS or UEFI firmware. That's like flipping the switch to say, hey, we're going to do SR-IOV here.
Okay, so the BIOS needs to be on board.
Exactly.
Right.
Then you usually get to decide how many VFs a particular PF should create. Sometimes you can set that in the BIOS, other times you do it through hypervisor tools or even OS commands.
So there are options.
Yep. After that, the PF driver in the host system or the hypervisor takes over. It uses special commands called APIs to manage those VFs, create them, delete them, the whole 9 yards.
So it's like a little VF factory.
Haha, in a way, yeah. But the system firmware has to get involved too. It's responsible for actually giving the PFs and VFs the resources they need, stuff like memory ranges, I/O ports, that kind of thing. And then when a VF is finally enabled, it gets its own unique ID within the PCIe hierarchy. That's the PCI Express Requester ID, or RAID. It's how the system keeps track of everything on the PCIe bus.
So it's a team effort right from the start.
Definitely. The BIOS, the host OS or hypervisor, the SR-IOV device itself, they all have to work together. And the PF driver is like the project manager, making sure everyone's on the same page.
All right, so we've talked about how SR-IOV is supposed to deliver better performance, and your sources spend a lot of time on direct memory access, or DMA, and interrupts. How do VFs handle those directly?
This is where SR-IOV shines. With SR-IOV, virtual machines can use their VFs to do DMA directly with the device's memory. That means a VM can read from or write to the device's memory without bugging the hypervisor for every transfer.
No middleman this time.
Nope. It's a direct line, and that makes a huge difference. Latency goes way down, and so does the strain on the CPU. But that's not all. SR-IOV also gives each VF its own dedicated interrupt resources. So when the physical device needs to tell the VM something, it can send an interrupt directly to that VM. Again, no hypervisor needed.
It's pretty clever.
It is. And the IOMMU, the IO Memory Management Unit, is crucial here. It makes sure those interrupts from a VF go to the right VM and nowhere else. This whole setup with direct DMA and dedicated interrupts, that's how SR-IOV gets those near bare metal speeds.
Okay, that IOMU keeps popping up. It sounds like it does more than just handle interrupts. Security and isolation too, right? So what exactly does the IOMMU do in the context of SR-IOV?
Spot on. The IOMU is a busy bee. Sure, it remaps interrupts, but its primary job in SR-IOV is to be the security guard, the bouncer at the club.
Keeping things in order.
Exactly. It does this by translating the I/O virtual addresses, the IOVAs. These are the addresses that the VMs use for I/O. The IOMMU takes those and translates them into the actual physical memory addresses of the host system. So a VM can only access the memory that's been specifically assigned to it, nothing more. That stops a rogue VM from messing with the host's memory or other VM's memory.
That's like a memory bodyguard.
That's a great way to put it. And as we said, it also handles those interrupts, ensuring they only go to the intended VM. Your sources also mention these other things, address translation services, or ATS and access control services, or ACS. These are like extra security measures at the PCIe level. If the root ports and switches support them, they help prevent unauthorized DMA transfers between VFs or even between a VF and its parent PF.
Like putting up extra walls to keep things separate.
Exactly. So the IOMMU is like a multi-layered security system. It ensures that even though VMs have direct access to hardware, that access is strictly controlled and isolated. No funny business allowed.
So it's like a traffic controller and a security guard, all in one. Now let's trace the path data takes. Your sources describe a big difference between how data travels in traditional virtualization versus SR-IOV, particularly for networking.
Yeah, totally different routes. In the old way, with traditional virtualization, any network traffic from a VM has to go through this virtual switch. It's a software component that the hypervisor manages.
More software in the mix.
Right. And the hypervisor has to look at every packet, process it, route it. That eats up CPU cycles and adds latency.
Not ideal.
Not at all. But with SR-IOV, things are much smoother. When you assign a VF to a VM, the network traffic for that VM can go directly between the VF and the physical network port of the SR-IOV network card. No more virtual switch.
A direct connection.
Yep. And a lot of SR-IOV cards have built-in hardware for sorting and filtering all that network traffic. They make sure each packet goes to the right VF based on where it's supposed to go. So the hypervisor does the initial setup, but after that, it's hands-off for data transfer.
And that's why SR-IOV gives such a big performance boost, especially for network-heavy applications, right?
Absolutely. It's all about that direct path.
That makes a lot of sense. And it seems like networking is where SR-IOV really shines. Your sources focus on that, especially for virtualized network functions. Why is SR-IOV so important for networking?
Yeah, SR-IOV is a total game changer for virtualized network functions, or VNFs. Think of it like this. You've got these traditional network appliances like routers, firewalls, load balancers. VNFs are their virtual counterparts running as software on VMs.
Well, instead of separate hardware boxes, you've got virtual versions running on your servers.
Right. But those VNFs need serious network speed. SR-IOV delivers that by giving them direct access to the network cards. And in data centers and cloud environments where speed and efficiency are everything, this is essential.
Especially with all the data flying around these days.
It's insane. And by skipping the hypervisor's software switching, SR-IOV lets these VNFs run much more efficiently and, get this, more cost-effectively.
So better performance and lower costs. Who wouldn't want that?
Exactly. Some high-end SR-IOV implementations can even handle crazy high bandwidth between VMs on the same server. And you often see SR-IOV used alongside other technologies like DPDK to further boost network packet processing. So for virtualizing network stuff, SR-IOV is often a key ingredient.
But it's not just about networking, right? Your sources talk about SR-IOV playing a role in high-performance computing, HPC, and data-intensive applications too.
That's right. Low latency and high throughput aren't just for networking. Think about HPC. You often need to move data really fast between computing nodes or VMs. SR-IOV can make that happen.
So it's about speed across the board.
Exactly. And in data analytics and machine learning, where you're dealing with massive data sets and powerful GPUs, SR-IOV can help optimize those transfers. Faster training for AI models, quicker real-time analytics. It can also improve how efficiently you're using those virtualized GPUs.
So it's making everything run smoother and faster.
Yep. Even industries that need real-time data analysis, like finance, they can benefit big time from SR-IOV's low latency. Bottom line, if you need high I/O performance and low latency in a virtualized environment, SR-IOV is worth a look.
And it's not limited to just network cards either, right?
Yeah.
You mentioned the possibility of extending SR-IOV to other PCIe devices like storage controllers and GPUs.
Exactly. Networking might be the main use case now, but the idea behind SR-IOV, that direct hardware access through virtual functions, it can be applied to other PCIe devices too. Imagine giving a VM a direct connection to a virtual function of the storage controller. Storage performance would go through the roof.
That would be amazing.
And for GPUs, SR-IOV could let you share a single physical GPU across multiple VMs, each with its own virtual function. They could all tap into the GPU's power for AI, graphics, whatever, without the mess of sharing it through software.
So SR-IOV is like a Swiss Army knife of virtualization.
Kind of, yeah. It's still early days for some of these other applications, but the potential is huge, and there's a lot of research going on.
Now, for all of this to work, you need the right software. Your sources talk about the software ecosystem, specifically the drivers for PFs and VFs. What do those drivers do?
Software is key. You need special drivers for both the physical functions and the virtual functions. As we talked about, the PF driver usually lives in the host OS or the hypervisor. It's the one managing the SR-IOV features of the device, enabling and disabling VFs, setting up shared resources, that kind of thing.
And what about the VF driver?
That one hangs out in the guest OS of the VM. It lets the VM talk directly to its VF like it's a physical piece of hardware. VF drivers are often streamlined, lighter versions of the full drivers you'd use on a bare metal system.
So they're optimized for this specific purpose.
Exactly. And sometimes, before the specific VF driver is loaded, the VM might use a more generic PCI pass-through driver just to recognize and interact with the VF initially. It's the combination of these specialized drivers that makes the whole SR-IOV thing work seamlessly.
And it seems like SR-IOV isn't some obscure technology anymore. Your sources point to pretty broad support across a whole range of operating systems and hypervisors.
Oh yeah, it's gone mainstream. You'll find support in most modern Linux distros, starting with kernel 2.6.3.0s and later. Microsoft Windows Server has it from 2012 R2 onwards, VMware vSphere version 6.5 and up, Microsoft Hyper-V since Windows Server 2012, even KVM, Xen, and Oracle Solaris support it.
So it's a pretty safe bet that most systems can handle it these days.
Pretty much, yeah. The industry's really embraced SR-IOV because it just delivers so much for virtualized environments.
So if someone wants to start using SR-IOV, what does it take to actually enable it? It sounds like more than just flipping a switch.
You got it. It's a multi-step process. It starts with enabling the IOMU in the system's BIOS or UEFI firmware. That's Intel VTD or AMD Vi, the technology that makes all this virtualization magic possible.
Right. Got to have the hardware foundation.
Absolutely. And in Linux, you might need to set some specific kernel parameters to make sure the IOMMU is actually active. Some hypervisors, like VMware ESXi, have settings where you explicitly enable SR-IOV.
Some extra configuration there.
Yeah. And of course, you need to make sure you've got the right PF and VF drivers installed in the host and guest OTZs. Plus, you'll probably want to specify how many virtual functions you want for each physical function.
So some planning is involved.
Definitely. And for the best performance, you might even need to tweak some settings in the guest OS. Stuff like how many receive queues the VF driver uses for network traffic. It's all about coordinating the firmware, the host, and the guest systems.
So it's not just software, right?
Yeah.
The hardware itself needs to be SR-IOV ready. What are the big hardware considerations?
Hardware compatibility is key. First things first. The network card or any other PCIe device you want to virtualize has to support the SR-IOV standard, the one defined by the PCIe specification. No SR-IOV support, no party.
Makes sense.
Then you've got the host motherboard chipset and the CPU. They both need to support SR-IOV and that IOMMU functionality, whether it's Intel VTD or AMD V. And as we mentioned before, the system's BIOS or UEFI has to let you enable these virtualization technologies.
So checking those specs is crucial.
Totally. And for the best isolation and security, you ideally want the PCIe root ports and any switches in the system to support those extra security measures, the address translation services, and access control services. Making sure all the hardware is compatible from top to bottom, that's step one.
Okay, we've talked a lot about the performance improvements SR-IOV can bring. Better throughput, lower latency, all good things. But are there any specific things to keep in mind when trying to squeeze the most performance out of SR-IOV?
Good question. So yeah, SR-IOV is inherently faster because of that direct hardware access, but there are still ways to optimize things like we talked about, getting those receive and transmit queues configured right, along with the interrupt settings in the guest OS. That can make a big difference.
So some fine-tuning can go a long way.
Definitely. And the performance gains you see will also depend on a few factors. How many VS you've set up, the specific features of your network card, and what kind of workloads you're running. Oh, and don't forget that SR-IOV also reduces the load on the host CPU, which can indirectly help overall system performance. The CPU has more breathing room to do other stuff.
It's like taking off the CPU's training weights.
Yeah. So SR-IOV gives you a solid foundation for performance, but some tweaking at the OS level can really maximize its potential for specific tasks.
Now, giving VMs direct access to hardware sounds great for performance, but what about security? Your sources do mention some security implications. What are the big concerns, and how do you address them?
That's a valid concern. Direct access does come with some security risks, but this is where our friend the IOMMU comes in, right? It's the one that keeps things locked down, preventing VMs from accessing memory they shouldn't. It enforces that isolation between VMs and the host.
So the IOMMU is really pulling double duty here.
Big time. And then you've got the SR-IOV network cards themselves. A lot of them have built-in hardware for filtering and isolating traffic. That helps prevent one VF from interfering with the others that share the same physical card.
So multiple layers of protection.
Exactly. But you still want to follow good network security practices. Things like VLAN tagging and network segmentation can further isolate your virtual machines. And the PF driver, the one in the host, it's got a big job monitoring and controlling what those VFs are doing, keeping an eye on things.
Making sure no one's getting out of line.
Right. And it's important to remember that there have been security vulnerabilities found in some SR-IOV implementations. So keeping up with security updates and patches is super important. The bottom line is, SR-IOV gives you that direct access for performance, but it relies heavily on hardware-based security features, especially the IOMNU, to keep those virtual machines securely isolated. You can't have one without the other.
So it's all about balance. Performance and security go hand in hand.
Exactly.
Now, managing an SR-IOV environment, that has to be a bit different than managing a traditional virtualized setup, right? What are the key things to keep in mind?
Well, with SR-IOV, you've got a few key tasks. Figuring out how many VFs you need, assigning those VFs to the right VMs, and then keeping an eye on their performance and resource usage. Luckily, most modern hypervisor management tools have features for all of that, whether it's through a graphical interface or command line stuff.
So the tools are out there to help.
They are. You might still need to use command line tools or even edit configuration files for some of the more advanced stuff. And the PF driver often has its own management interfaces, and it can give you stats on the VFs. Now, one thing to consider is live migration. Moving running VMs around is a big deal in virtualization, but when those VMs have VFs assigned to them, live migration can get tricky.
Because of that direct hardware connection.
Exactly. It might be more complex or even not supported at all in some SR-IOV setups. So knowing what your hypervisor and hardware can handle is super important for managing SR-IOV-enabled VMs.
So doing your homework beforehand is crucial.
Definitely.
Okay, to really nail down the differences, can you give us a quick comparison of traditional PCIe in a virtualized environment versus PCIe with SR-IOV?
Sure. The biggest difference is where the virtualization happens. In the traditional way, the hypervisor is the one doing the virtualization, all in software. It pretends to be the physical device for each VM. So it intercepts every I/O request from the VM and translates it for the actual hardware.
Lots of software involved there.
Yep. But with SR-IOV, the virtualization happens right in the PCIe device itself, in the hardware. It's got those physical functions for management and the virtual functions that can be directly assigned to VMs. And the VM sees its VF as a separate physical device.
So in one case, the hypervisor is doing all the work through software. In the other, the hardware itself is handling the virtualization.
Exactly.
And what are the main trade-offs between these approaches? Performance, resource sharing, complexity, live migration.
Okay, so performance-wise, the traditional way usually means higher CPU usage, more latency, and slower overall throughput. All that software emulation takes a toll. But SR-IOV gives you lower CPU usage, less latency, and much faster throughput, often close to what you'd get with bare metal.
Night and day difference, then.
It can be, yeah. Then there's resource sharing. In the traditional way, it's the hypervisor's job to share the physical device among the VMs. That gives you flexibility, but it can also lead to performance bottlenecks. With SR-IOV, you divide up the physical device's resources into those dedicated VFs. Each VM gets its own slice. And the IOMMU makes sure everything's isolated at the hardware level, which is great for security.
So it's a trade-off between flexibility and performance.
Yeah, kind of. Then there's complexity. Traditional virtualization is usually easier to set up because the hardware requirements are simpler and live migration is generally smoother. With SR-IOV, you need specific hardware that supports it, and live migration can be more complicated or even impossible in some cases.
So it's not a one-size-fits-all solution.
Definitely not. You need to choose the right approach for your specific needs and what you're trying to achieve.
That's a great overview of the key differences. Okay, as we wrap up this deep dive, what's the big takeaway about SR-IOV in the world of virtualization today?
SR-IOV is a huge step forward for I/O virtualization. It tackles those performance limitations that have always been a headache in virtualized environments.
And it does that by giving those VMs a direct line to the hardware, right?
Exactly. By minimizing the hypervisor's involvement in the data path, you get close to bare metal performance. And that's critical for applications that need very low latency and high bandwidth. It opens up a whole world of possibilities for virtualization.
So it's making virtualization a more viable option for even the most demanding workloads.
Absolutely. And as data centers and cloud environments become more complex and demanding, SR-IOV is only going to become more important. It's likely to be a core technology in the future of virtualization.
And with hardware and software constantly evolving, who knows what new capabilities and applications will emerge for SR-IOV.
Exciting times ahead for sure.
So here's a final thought for you, our listener. If SR-IOV can create this hardware-level shortcut for I/O, what other areas of computing could benefit from similar techniques? Where else can we use hardware to bypass those software bottlenecks and make things run more efficiently? This deep dive into SR-IOV really shows how we're constantly pushing the boundaries of how we manage physical resources in our increasingly digital world. Thanks for joining us today.